Go. All right, folks. Welcome to week 11. We're almost done. We're almost there. Today's topic is one of those strange topics in database land. It's probably one of the most important, not, select star from table type topics. It's one of the most important ones in general when you're talking about databases being used in business. And it's the topic of transactions. And transactions is an interesting topic to teach because it's one of those topics you either spend, half an hour, 45 minutes talking about it, and you teach everybody how to use them, or you spend an entire semester on it, explain the magic math that happens on the inside. I'm going to give you a guess which flavor you guys are getting. This is why you want them, this is how they work, and then I'm actually going to sit down and do a demo, my first one in this group for the semester. I'm actually going to be typing stuff in today. Yay. All right. So transactions. We'll start with the definition just so that we're all talking the same thing. A transaction is an action or a series of actions carried out by a single user or an application program which reads or updates the contents of a database. Insert statement, update, delete. You fire off a single row of that, it's a transaction. If you do multiple rows of that and you don't explicitly mark it as a transaction, it'll be multiple transactions. So if you do 6 inserts, but you don't tell the database server to treat this as a single thing, it'll be 6 transactions. Some database servers, will be in transaction mode by default. Oracle, for example, is transaction mode by default. You don't have to tell it to act like that. So the true definition of a transaction is a logical unit of work on a database. So each transaction does something into the data in the database, and the rule is that no part of it alone achieves anything of use or interest. In other words, it's a multi-step. Could be just one step, but it usually has multiple steps when we talk about transactions. So transactions are known as a unit of recovery, consistency, and integrity. And before I start talking about the acronym here, transactions are important because it ensures that your data doesn't get corrupted, that your database is in a sane state before you start, and it's in a sane state once it's completed the work. I'm pretty sure I'm actually going to have an example of this somewhere in the slide, but I'm going to do it now. The best example of a transaction is transferring money from one bank account to another bank account. So you got 2 bank accounts, a checking account and a savings account, right? So Canadian banking terms. And you need to move money from, say, your savings account into your checking account because you ran out of money, you got to go buy groceries. So you're going to dip into your savings. When you transfer money from savings to checking, there's multiple steps to that. Most people say, I just transfer like 20 bucks across. Yay, go to buy myself a burger. However, there's actually multiple steps because one account goes down by $20, one account goes up by $20. It's impossible to make both those things happen at the exact same time. Therefore, depending on which bank you're talking about, because they don't all do it all differently, but they do it one of 2 ways. As part of the transaction, they'll start the transaction block saying, hey, everything I'm about to do counts as one thing. It's going to go savings minus 20. Then it's going to take checking plus 20, and then it'll commit the work. If either of those steps fails, the whole thing fails. That's a transaction. Because you don't want to have the case where you took $20 out of an account, and then the whole thing fails, and suddenly you get $20 just disappear. Just gone into the ether. The same thing with the other way around where, you go, you add 20 bucks somewhere, but you didn't take it from somewhere else. Suddenly you just invented $20. Transactions make sure that this kind of thing doesn't happen. And when we talk about transactions, there is an acronym. It's called ACID. So ACID has 4 concepts in it. Atomic. So A transaction is considered atomic. In other words, whatever you decide is in a transaction cannot be subdivided. Even if it's multiple steps, it's all treated as one thing. Something is atomic because you can't split it. Because you know what happens when you split an atom. Therefore, it's atomic. In other words, it's its most basic piece. It cannot be broken down. Consistent. That means that the database is in a consistent state before you start. And once a transaction is completed or aborted, it's still consistent. In other words, going back to my $20, you didn't make $20 disappear, or you didn't manufacture $20 in the process. If one account had 100 and the other one had 0, total's 100, right? And then you transfer $20, so then suddenly you've got 80 and 20, it's still $100. It's just broken up into two places. That's what they mean by consistency, that whatever's there before and after, it stays consistent. I mean, there's other things like creating an order, and you create an order that's consistent unto itself, but that's just examples. Isolation. While a transaction's in progress, it's invisible to the rest of the database server. There's some rules where it's kind of not invisible, but essentially as far as everybody else is concerned, like if you're doing something and he's doing something, he can't see what you're doing and you can't see what he's doing. And at the end, they just get reconciled with each other. Durable. Once a transaction is completed, committed, and checkpoint, it can never be undone. It's permanent. Again, you transfer money from one account to the other account and then the computer shits the bed while that's happening. The job wasn't completed, therefore it's not durable. But if the job was completed and then the server dies, everything that happened just till, the previous moment should still be there. That's durable. So asset. By the way, that will be on the exam. Just so you know, this particular acronym will show up on the exam. Okay. Heck, I just finished explaining all this. Here's the long versions. An atomic transaction can't be executed partially. It should be totally self-contained. It's not broken apart. Even though if it has 25 steps, conceptually, it's one task. It's one unit of work. It cannot be broken down. Consistency. No, this database is stable. You do stuff. You're done. It's stable. What's in the middle might not be stable. But the starting and the end point should be stable. Like, for example, transferring money. One of the two steps in the transaction is you took money away from one account. Therefore, at that point, the database is not consistent because there's $20 just floating around somewhere. And then it gets added to the other one, then it gets completed, then it's consistent again. Isolation, I already explained that, where two people are working, but they can't see each other's work. And durable, once the server writes the data, it's good. And here's the example about transferring money. I knew I had an example in the slides of this. So for the atomic atomicity, I just have a hard time saying the word atomicity, so I can't say it a second time. I get it right once. So an atomic, for something to be atomic, you shouldn't be able to take money from A without giving it to B. That's atomic. In other words, it all has to work. Consistent. Money isn't lost or gained. Isolation. Other queries shouldn't see the fact that there's money moving around until it's done. And durability. After you put the money in B, it doesn't magically show up in A again. So suddenly you've manufactured money again, right? Took 50 from A and gave it to B, and then something goes wrong and suddenly A has 50 and B has an extra 50, so you just invented another $50. That durability means the money doesn't magically reappear because it's consistent. All right. So in database servers, there's something called a transaction manager, and every database server does this slightly differently. But they all have something called a transaction manager. So they use row locks and timestamps to ensure consistency so that they know when things are happening, especially if there's concurrent transactions. I don't know why that says next lecture, because that's all covered in this lecture today. So concurrent transactions mean I am paying a bill out of my account, and as I'm paying that bill and the transaction's happening, an auto withdrawal happens, right? But what it does, it'll use the timestamps on the lock to make sure that they don't interfere with each other. So whichever one started first wins, then the other one's applied after the first one finishes. A log is kept in ensure durability. So when you have transactions running, what happens is, remember last week when I was talking about backups, I was talking about the bin log, where it writes out every command? So the way the transaction works is it takes the command, writes it into the log, then it applies it to the data, and then it marks the log as being completed. So every command you do in a transaction gets written out to a file before it gets written to the database. And why would you want to do that? Because writing the command to a file is way faster than writing to the database. And if something goes horribly wrong, the database server knows what commands have been run and which ones need to be run to fix itself. The transaction manager enforces the asset properties. It schedules operations of transactions, so every so many milliseconds it does things. And it uses two commands called commit or rollback. Commit means it's the end of the transaction block and everything is good, so you're now allowed to write it to the database. And rollback means you've reached the end, but something went wrong, so undo. So if you guys remember when I talked last semester about, there's no such thing as undo. There is if you're using transactions. You can undo the transaction by issuing a rollback. And rollback means roll back to wherever you saw, the last begin statement. Rollback signals unsuccessful end of a transaction. Of course, I just talked about it on the previous slide. Unsuccessful end of a transaction, changes made should be undone. It's as if it never existed. Commit says it worked, write everything out to the disk. Okay, so another thing about transactions is that it allows you to recover your state of your database within reason. Now, like anything else, prevention is better than the cure. Transactions are good to prevent bad things from happening. That's what they're for. But sometimes you want to make sure there's, things in place to make sure you don't need to rely on the fact that transaction probably will recover your situation. You should use a reliable operating system. In most enterprises and data centers, a lot of database servers are running on Unix. Not Linux, Unix. It's, it used to be good. Then Oracle bought it. For example, AIX from IBM is one. It's a Unix, actually one of the few Unixes left. HPUX from HP is another Unix, runs on their mainframes. There was a bunch before. Digital Equipment had their own version of Unix. Microsoft has a Unix license. They don't sell it, but they have a Unix license. There is a free Unix for people to use. That's the BSD flavors, FreeBSD, NetBSD. And this is one of the few times I don't make fun of Mac users. Technically, they're running Unix. Under all the lockdown and the inability to change things, and all the pretty eye candy, below that is Unix. It's actually running FreeBSD, from before they took it and forked it. Failing Unix, you probably want to run, an enterprise grade flavor of Linux. So Red Hat Enterprise, SUSE Enterprise, Ubuntu Server if you have to, with the enterprise features turned on. You want to have good security. We talked about that, so not a lot of worry about that. UPS and surge protectors. You want to make sure there's a power outage, your server has a chance to shut down properly. And you also want a surge protector to make sure if lightning hits a pole outside, it doesn't fry your server. RAID arrays. Those are redundant array of independent disks. That's what RAID stands for. So you'll have, lots of disks in a server and they mirror and copy data to each other. RAID can improve performance, but it's usually meant for safety and redundancy. Like for example, in my home lab, I have a home lab at home, because I'm a nerd. Um, I have a RAID 5 array connected to my home lab server. I've got 4 disks plus one for fail. So if I can lose any of those 4 disks at any time and I lose no data, I lose 2 disks, I lose everything. But I can lose 1 disk and I lose nothing. And there's a hot standby where if one fails, it'll switch over to the spare and rebuild the array there. Then I can swap out a bad disk. Database servers often store their data on a RAID array just for safety. You can't protect against everything, obviously, because you can't avoid crashes, power failures, physical hard drives dying. People say, oh yeah, well, we're all going to SSD and NVMe drives and, solid state memory. They're not any more reliable than hard drives. Like people talk about, oh yeah, solid state, there's no moving parts. Yeah, but they wear out faster. The memory chips wear out. So when you buy like a 1 TB SSD, did you know they're actually 1.2 terabytes? People don't realize there's 1.2 terabytes. That 200 gigabytes is hidden from you. And as memory chips wear out, it starts allocating memory into that 200 gigs. So, and I know this is how it works because at my old job, we had one SSD that died. And one day the guy booted up, he goes, my terabyte drive is now 760 gigs. I go, oh, that's cool. The next day it was down to like 650. The drive was literally dying and it was running out of memory, so it was reporting smaller amounts of space. And an enterprise drive, that's not a good thing because it's not a good thing. Now, mind you, enterprise SSDs are a lot more reliable than the ones you buy in laptops or your desktops because you're going to pay $10,000 for like 4 terabytes of space. But they're not any more reliable realistically than spin disks. Because a spin disk that is spinning, that doesn't get hit, doesn't get beat up, doesn't have a sudden crash, will keep spinning until they get powered off, and then you have problems. But we had a server at my old job, the drive in it was on for 20 years, and it still worked until we moved. Then they turned it off, and then it didn't come back. Because it was worn out. It's just as long as it was spinning, it just kept going. User mistakes, sabotage, natural disasters, and I talked about database recovery, right? So the transaction log. The transaction log records the details of all transactions. Makes sense. Any changes the transaction makes to the database, it also keeps track of how to undo these changes. When the transaction is completed and how it completed. In other words, did it finish or did it fail? Like, did it finish successfully or did it fail? The log is stored on disk, not memory. It's never in memory. So this log file is in append mode at all times. So the file is always open. And every time you do an insert, an update, or a delete on a table that supports transactions, it adds the command you did to the end of the file instantly, like that. So if the server crashes, like there's a blue screen of death, it's not sitting in memory because it's been written to the disk. And it's a write-ahead log. So it writes to the log before it tries to do the work against the database. And the entry in the log must exist before the commit statement processes. So it will make sure that every step you did is in the log before it will ever try to write it to the database. There's system failures. And this is the part where some people have struggled with some of the concepts. We're already sure I got the slide I need in this. At various times, databases take a checkpoint. You might have remembered about 15 minutes ago, I did say the word checkpoint. So a checkpoint is you write the changes to the database, insert, update, delete. It writes it to the write-ahead log, then it applies it. The thing is, it's only applied in memory. The checkpoint is when it takes the results of what's happening in memory and then it puts it on the disk. So a checkpoint is when it gets committed physically to the drive. whether it's a single row, 100 rows, a million rows, whatever, there's a checkpoint that fires off every so many milliseconds. And when that checkpoint happens, it writes to the disk. So it's dumping it's like an autosave. You know, you're working in Word, and you'll notice every once in a while say autosave, autosave, autosave as you make changes because it's keeping track of the work. It's checkpointing. It's just happening every, say, 5 or 10 seconds or whatever. So if there's a system failure, it means that all the transactions are affected that are running, whether it's software crash or power failure, and as long as the physical disks, the hard drives, are not damaged, it will attempt to recover. So what the cool thing about this, the way this works is, so you have a power out. So you have a series of transactions. They're written in the write-ahead log. And then just before the checkpoint, something happens. Power outage, server shits the bed, whatever, and think your pick. Something just dies, right? Power supply blows, whatever it is. So you fix the situation and you restart the server. When the database server comes up, it'll look at the write-ahead log and start processing it. And it'll go, hey, this was the last checkpoint, so now we're going to read the next things that have been marked as it managed to do it, and it'll replay those transactions to bring the server back up to state, and then fire off another checkpoint. So that's the point of the write-ahead log, is if the server completely dies, and something's not, and it was completed successfully, but it never made it to the disk, the write-ahead log will know when last time the checkpoint happened, and it'll replay any transactions that should have happened. So on the reboot, it fixes itself. So pretty smart people that wrote the database software. Okay, so here's a graph, and am I going to actually show this as it goes through? Yes, okay, good. So this is a chart. I've got 4 transactions. I'm going to actually go through these in a second. So any transaction that was running at time of failure needs to be undone and restarted. So that's, needs to be fixed. Any transactions that were committed need to be redone. So let's say this transaction that's running but never finished, and then the server fails. Those are undone, right? Because they should not be done because they never finished. Anything that finished successfully but was not checkpointed needs to be redone. So those are redo. So I'm going to go through the chart in a second. So we need to remember undo and redo as we go through the next couple of slides. Undo means undo anything that didn't finish since the last checkpoint. So I can use video game logic for this one. You're playing a single player game and it has checkpoint saves. So you can save normally, but then there's also checkpoint saves. And you reach a checkpoint and then you die. Then you respawn at the checkpoint, you die right away because the game saved just as you're getting headshotted. That has never happened to me, ever. So then you have to load an older save, right? So the checkpoint in the game where you keep getting killed, it goes on the undo pile because you're going to recover from previous save. And then you got the redo list, which when you start transactions is actually empty. It starts empty. So for each entry in the log that we're going to be talking about, starting from last checkpoint, if a begin transaction entry is found, it's added to undo. Once it's committed, it moves from undo to redo. All right, so the current state of this database, you'll see that there's a green line that's going to move on the slide. You see me moving through the slide, you see a green slide moving, a green line. So the server is currently at a checkpoint. Transaction 1 was started and completed. That is it's going to be it doesn't need to go anywhere because it's already been checkpointed. Transaction 2 and transaction 3 were both started before the checkpoint. So currently, 2 and 3 are in the undo pile because they didn't complete before the checkpoint. So they didn't complete before stuff was written to the disk. So at this point, we have something called active transactions. Transaction 2 and 3 are currently active, and there's nothing in the redo pile. So now the checkpoint is passed. Transaction 4 starts. So we have 2, 3, and 4. So currently we have 2, 3, and 4 in the undo. They're all active transactions. Transaction 5 starts. So now we have 4 transactions in the undo pile. Transaction 2 completes. It finished. It's successful. It's been committed. So a commit command has happened. So transaction 2 goes from undo into redo because the checkpoint hasn't happened yet, right? So the new checkpoint hasn't happened. So transaction 2 is in the redo pile because it managed to finish the job. But it hasn't been written to the disk, so we know it's successfully finished. Therefore, if the server needs to recover, it needs to redo that command. Transaction 4 completes, gets committed, it gets added to the redo pile, taken out of undo. And I knew I was missing a slide. The next slide is, we hit the failure. So imagine the green line is now here. Failure, somebody was behind the server and they were doing maintenance on another machine and they accidentally pulled the power cord. Server just turned off. At this point in time, we have 2 transactions in undo and 2 transactions in redo. When the server comes back, it needs to undo 3 and 5 and delete them from the log. It needs to redo 2 and 4 because they were successful. So log recovery is interesting because it works from both ends at the same time. It reads the transaction log from the front and the back at the same time. So it looks at the checkpoint and it starts working forward. And it looks at the transactions that need to be redone. It'll redo those transactions. At the same time, it's working from the back for any transactions that were incomplete and rolls those back and undoes them. So when we talk about forward recovery, it means we're doing all the redos one after another in the order they finished. And the backward one means we undo anything that went bad. And it'll return everything in a consistent state. Media failures, you guys know, I already talked about that. Backups, we talked about that too. So I actually talked about this last week when I was talking about backup restores, right? So when you restore a database from the last backup, and if you are using a binary log or a transaction log, you could theoretically replay all the commands for the day from the transaction log for that day until the next backup. And that way, if you lose the database server after the backup, but there's actual valuable data in it, you can still restore it from that. If the transaction log is damaged, obviously you can't replay the transaction log. So as a rule of thumb, you put the transaction log on another disk, reduces the risk of losing both. All right, concurrency. So large databases are used by many people, obviously. Look at your bank, right? When you do a transaction at the bank, you're not the only person playing with money at that moment. Millions of people are playing with money at that moment. So many transactions need to be run in the database at the same time. And you want them to run at the same time. Otherwise, we have problems. So we need to preserve isolation. Again, you're doing something, he's doing something. As long as you're not interfering with each other, you should both be able to do your stuff at the same time. Right? The only time we have a problem is when you're trying to access the same data at the same time. So if we don't allow for concurrency, then the transactions are run sequentially. That used to be how transactions were. So you would lock the whole table, and then you do your thing, then he gets to do his thing. Even though you're not touching the same data, he'd have to wait for you to finish. Just like when you go to the bank and you're standing in line, right? You can't go talk to the teller until the person ahead of you is gone. You have to wait your turn, and that's what's called sequential. Ideally, you have a dozen tellers open, and then people come and just go to the next available teller. You do what you need to do. Person next to you does what they need to do, and everybody's happy. Long transactions, for example, a lot backup makes everybody wait. I've had the case where I've gone to the bank where they only had one teller, and the person ahead of me was doing business transactions, not personal transactions. They were doing they only had the business teller open that day for some unknown reason, and I had to wait for half an hour for the person to finish. And I didn't have a choice, I had to wait. It's something I couldn't do at the ATM. So it was gross. So long transactions make things wait, so we want concurrency. So in order to run transactions concurrently, we need to enter or leave their operations. In other words, you take a turn, he takes a turn, you take a turn, he takes a turn. So each transaction gets a bit of computing time. Sometimes you end up with lost updates if you both try to change the same thing at the same time. If he started like a millisecond before you, his will finish, but then yours will overwrite it. Then you have a lost update. Uncommitted updates. It could be that, again, he started his, you started yours, his got committed, yours didn't. Incorrect analysis. So inside the server itself, it runs, most servers run an analytics on itself to say what's behaving well, what's not, and then it can take, some corrective measures on its own. And often this happens because when the isolation gets broken. Okay, so that's the theory. Let me demonstrate. It'll make so much more sense when I demo. Take my word for it. That was a lot of words for something that's actually really simple to see in practice. And I'm using MySQL Workbench because my copy data grip, my license just stopped working today for some unknown reason, so MySQL Workbench it is. So for this demonstration, I need to actually establish two connections. You can do the same thing in MySQL Workbench, in data grip, where you open up two, you go right-click, new connection, right-click, new connection. It's the same idea. So I'm going to create a new database because I don't have a database for this. So I'm going to go create database transaction. I cannot type today. Demo. Use transaction demo. Okay. And now if I refresh on the left, you'll see transaction demos here. So this connection is connected transaction demo, and I'm going to refresh. And this one's also connected to transaction demo. So I've got two connections going to the same database. Easiest way for me to demonstrate this. Okay, now I'm going to create a table. Table 1, because I only need one. ID, INT, auto increment, primary key. Number, car 100, because I want really big account numbers, and I'm going to go balance, and it's going to be numeric 10,2. And create table, should have the word table. Okay, so this is a MySQL special. Let me make this a little bit bigger. Okay. It's decimal. Can you tell I've been working in Oracle lately? This is a MySQL special. You'll notice it says engine equals NODB. In MySQL, the default table type, at least it used to be, was MyISAM. MyISAM does not support transactions. So just MySQL. All the other database servers don't do this. You have to tell it, hey, I want you to use a database engine that supports transactions. Otherwise, it'll tell you, hey, I started transactions. Hey, I committed a transaction. It didn't do a transaction. Okay, just so you know. And I'm going to create my database, my table. Okay, my syntax was good. I'm going to refresh here. You can see that the table exists. And I'm going to refresh. It doesn't even make a difference where I'm doing this. I'm going to refresh this one. The table is there. Fantastic. Okay, so I'm going to go to connection 1, and I am going to go to start an actual transaction, a true transaction. You go begin, or you can go begin transaction. So you can either use begin or begin transaction. I use begin because I just prefer begin. And I'm going to go insert into that I call my table. Table 1, because I'm so original. Insert into table 1. Account number and balance. And values will be A1. And the balance is $99.56. Okay, so I'm going to take the whole thing and go run. Cool, I did an insert statement. It ran. I'm going to go to my other connection. So I'm demonstrating isolation rate. So if I go select star from, and go select star from table 1, there's nothing home because it's the other connection. So I just created an account with a balance in it in connection 1, and I started a transaction. Because the transaction has not been committed, it's not visible to the rest of the world. So now I'm going to go and commit it. And I'm just going to run the commit statement, not the whole thing. Okay. Again, it just says, hey, congrats, something happened. Now if I do that in the other connection, and that didn't work. What? Did I fail my insert? Begin. Go. Run. There it is. There it is. Okay, I have no idea what just happened. I've done this demo many times, and it's the first time it's ever been blinked like that. So, like I said, actually, you know what? I'm going to put the select statement inside my my thing here. So I'm going to go account 2, and this one's got $199.52. Okay, so I'm going to run this. I haven't done the commit yet. You can see that it's there. I go to my other table, but it's not there because it's still isolated. So now if I commit it, and I come here and I go run, it's there. Now the commit's behaving like it should. So this is isolation. So what's happening in connection 1 is not visible from connection 2 until a commit has happened. If I can go do another insert, so account 3, and this one's only got $9, and I choose to do a rollback instead. So I'm going to start the transaction and run it. You can see that it's here, right? Now I'm going to do a rollback. And I am going to come here and show you guys that the data is now gone. So I'll run this. I'll run the whole thing. So it'll show 2 tabs at the bottom. So tab 1, there's the insert. Tab 2, the insert is gone because I chose to undo it. I rolled it back. In the meantime, my second connection never saw it. It's like it never even happened. So that's isolation.
You don't need to commit. It doesn't need to commit for you to do a rollback.
No. You either commit or you roll back.
Okay.
You either say, yes, this is good, or you undo. So the commit or the rollback marks the end of the transaction. You commit if it's successful, roll back if you fail. Most database servers have automatic rollback, where if you start a transaction and something goes wrong, it will roll back the transaction if an error happens because it failed. There's ways to make it do stuff past that, but that's much more complicated. Now, remember earlier I said as long as you're not trying to touch the same data, everything is good. Now, instead of doing an insert, I'm going to do an update. Update table 1. Set balance equal to 1950. Where it's equal to 2, so where ID is equal to 2. Okay? So I'm not going to put in my commit statement yet. I'm not going to do anything else. So I'm just going to show you guys right now that account 2 has 199.52. That's where I'm starting. So there it is, 199.52. And the first one, I'm going to begin my update. Prove to you that yes, the person just spent, $170, $170. And over here, you can see that, the money's still there. However, I've begun a transaction and I haven't committed it. Okay? So now I'm going to go to the second one and I'm going to try to change its balance to 50. So one is running and not committed. So the table's locked. So I'm going to try to update that row. I'm going to go run. Notice down here, it's really small, but it says running and it doesn't know what's happening. Why? That's because currently this transaction has that row locked. It says, I'm doing stuff to this row. I haven't committed or undone my changes, so you're just going to have to wait your turn. So now I am going to roll back my change. Roll back my change. Go. Okay, so I rolled it back. Now if you come over here, well, it took too long. I talked, right? It says it lost a connection. So let me do this again, really quick with less talking. So begin. Try to do this. It's running, and I roll it back. Go. You'll notice here that it says it finished. So if I go select star from table 1, and I do this, it's $50 because I changed it to $50. Now, if I come here, and this is when I was talking about a lost update earlier, when you got 2 transactions touching the same thing, and they have to happen one after another, I'm going to change this to commit. Commit. So I'm going to do the first part, just like before. I'm going to run this. I am going to try to run this. It's not letting me. Now I'm going to commit it. And now what's my balance? Is it going to be 1950 or is it going to be 50-50? The balance is going to be 50-50 because this one started and committed, but this one started after the first one. So then, because it started after the first one, it's going to take that change as the winner. So that's just showing you guys that, yes, you can have multiple transactions touching the same record at the same time, but the last one that started is going to win. Now, MySQL is a little extra because it does row locks. In other words, it only locks the row. So if 2 people are trying to change that row, too bad. If other database servers such as Postgres or Oracle, they support column locks. So only the column that's being changed will block another transaction. So for example, you're updating your customer record and you're changing your phone number. In the meantime, somebody else is modifying something else on your account. Maybe they're, approving you or whatever. Those transactions can happen at the same time because they're not touching the same data. With MySQL, it's the whole row. You can't touch the row until the other person's done touching that. So, but yeah, that's transactions in practice. It's very straightforward. You begin, you issue multiple commands. And in this case, I only did one, but I could go ID 1, that one. They got paid today. Got big payday. And in Siri, we could do an insert here if we wanted. insert into table 1 count number, balance, values, A4, like this. And I could run all this as a single block. You can see it's all happening there. I come here. You don't see any of these changes. I commit my change. And now they're all there. That's a transaction block where you're doing more than one command. So transaction blocks are powerful because you can group. So an example of a good transaction would be a person has a shopping cart. They're on your website, right? And they've put like 5 things into their shopping cart, but they haven't checked out yet. When they go to check out, you need to make sure that not only the order gets written, but all the order items get written too. So you'd start a transaction, you'd insert the order, then you'd insert each of the order lines, and then you would commit. If any of that fails, the order should not get created in the system. That's what transactions are for. And can you guys guess who created transactions in a computing world? Just a fun piece of trivia. Okay, pardon? Banks. There was a data scientist at banks that created them, where they worked with the big database vendors. So back then it would have been Oracle and IBM. They worked with those database vendors to add things such as transactions. So the data scientist said, what the bank said, we need this. The programmer said, cool, let's go figure out how to make that happen. And apparently had some really smart people that figured out how to make it happen. But yeah, it was basically the financial world is what pushed for transactions for obvious reasons. Okay. So that brings us to the end of today. Again, a 1-hour lecture, 47 minutes as usual. Next week will be a little bit longer-ish. We're talking about functions and triggers next week. So we're talking about programming. SQL is not programming. SQL is just asking questions of a database. We're going to be programming. I'll be teaching you guys some programming. Actual for loops and variables, but inside the database server with its own language. It's a really cool topic. So it's going to be a little bit of a beefier lecture. But the other good thing is that's the last topic of the semester. So after next week, we're done new topics. The week after that will be review. And the week after that, I'm not sure. We're going to get there. But next week is the end of the content. And it's a good one. A fun one, I guess. Well, at least, you guys know what loops are, and you know what variables are, and you know what conditionals are. So I don't need to teach you guys those concepts. I've taught this at level 1 where I actually had to explain some of this stuff. So yeah. All right. So that's the end.